What's the magnitude of that force? 900 newtons. So I just draw a straight line marking 900 newtons on the plot. Does this make sense to everybody? My next question, I have to go from 0 to 3. Okay, so here is 3 meters, 6 meters, 12 meters. How do I go from 0 to 3? I have to look at the slope of the shear force diagram. The slope of the shear force diagram, always understand, is equal to the load intensity with the proper orientation of the load intensity between 0 and 3. Right before I hit this force of 300 newtons, there is no distributed load, which means that I have to travel as a straight horizontal line of 0 slope. Okay? Am I making sense here? No calculations whatsoever. What's my next step? Yes.
You're going to drop down 300.
Absolutely. Fantastic. I'm going to drop down 300 reduced from here. So I'm going to stop at 600 newtons. Why am I dropping down by 300? Is because I see that there is a concentrated force acting here. The force is directed down, and so it's pushing me down. If I see a force pointing up, pushing me up. If I see a force pointing down, pushing me down. If I see a distributed loading, it will align me in some direction. Okay? Then easy journey ahead, 3 meters, all the way to 6 meters before the start of the distributed load. What do?
Constant 0.
Straight line.
0 slope, straight line. Then comes the clincher. So this is 3, this is 6. I am currently at 600 newtons. I have to check and see if I calculate the area of this triangular distributed load, is it giving me 600 newtons? What's the area of this triangular distributed load? Half times the base times the height, which is obviously going to give me 600 newtons. With a negative sign because the intensity of the load distribution is pointing down. So I am starting at 600, gradually taken down to 0. So my calculations work out. We did not do any calculations besides doing the support reactions. Absolutely nothing whatsoever. So I know I got to come back home to 0. Everything is working out beautifully. How do I go home? Yes?
Negative increasing.
Fantastic. So the slope is negative because the intensity is pointing down, and it is increasing in magnitude because I'm seeing that I'm starting at a 0 slope. Look at this. Starting at a 0 slope here, and then increasing all the way to a slope of 200 newtons per meter. Okay, so 0. And because my slope is changing linearly, my curve becomes a quadratic. Slope was 0 here, slope is increasing, and it's a quadratic curve because my slope is changing linearly. Am I making sense to everybody? What did we do? We did not do anything. The only thing we did was statics. Everything else is just looking at what we did and analyzing it directly. None of those x is equal to 0 minus and 0 plus nonsense. Does this make sense to everybody? I want to pause and see if there are any questions before I draw the bending moment diagram, which is slightly more tricky. It might involve some calculations. Is this question?
So for the last part of it, in the bending moment diagram, is it going to be cubic then?
Absolutely, absolutely, because the slope is changing in a quadratic manner for the bending moment diagram, because the slope of the bending moment diagram is the shear force value. see if there are any questions. If you want to draw the bending moment curve next, it's much more interesting. All of us are on the same page. Just to recap, I start off by seeing an upward jump because I see a force of 900 newtons pushing here. Then between x is equal to 0 and 3, I see nothing going on, so nothing special is happening in my life. I just travel along a straight line path, rectilinear motion. Simple stuff, right? Then I come to this guy. I'm seeing that it's pointing down, which means I have to decrease by that amount from where I was. So it takes me from 900 to 300, pushing me down. Singularity taking place in the free body diagram, concentrated force. Then I trundle along with abandon from here to there because there is nothing taking place. Then suddenly I see that there is a distributed load. If you have a distributed load, it will gently take you home or it will gently take you somewhere else. How do you go from where to where? From here to there is by looking at the intensity of the load distribution for the shear force diagram. It starts at 0. So my slope starts at 0 here. My slope increases because the intensity of the load distribution increases, but the slope itself is negative. So I'm going to go from 600 newtons all the way to 0. How do I know that I'm going to 0? The area of this guy should be equal to the magnitude of 600 newtons. Now let's do the bending moment, which is a little more challenging. Okay? So I need this, I need that. Let's maybe draw it underneath here. Just to give it some change. All right, bending moment curve. Help me out here. At A, what happens? Yes?
Negative jump.
Negative jump. Why is it negative? It's because this is a counterclockwise couple moment acting at that point. So I'm going to drop down to 6,900 Newton meters starting at A. All the way from here. Negative. And M is in Newton meters. Then how do I go from 0 to 3? And what's the value? The value of the bending moment at the last point that you are interested in, for example, if I'm now looking at the point 3, is the area under the shear force diagram plus this quantity. So the area here, all of that is a rectangular box which is positive. Okay, so that's going to be 900 times 3 minus 6,900. So minus 6,900 plus 900 times 3 is the value of the bending moment at x is equal to 3 meters. Am I making sense to everybody? I'm not doing calculations as much, but I still need to do some. So minus 6,900 and then 2,700.
4,200.
4,200, thank you. So I have to go to 4,200. How do I go? I have to look at the value of the shear force. The slope of the bending moment diagram is equal to the value of the shear force, which is positive and constant. So my bending moment has to go linearly from 6,900 to negative 4,200. Okay, so I'm going to go linearly. Does this make sense to everybody? I want to make sure that I'm on the same page as all of you. We don't want to do extensive calculations. Now, who cares about numbers and calculations? I want to see a figure, just depict it mentally, and then write out these things with limited calculations. I mean, of course, I have to find the support reaction. You can't do away with that. Help me out. How do I go to this point and what's the value there? At x is equal to 6 meters, the value of the bending moment is going to be this area, which is a rectangular box, plus negative 42. Okay, so that's going to be minus 4200 plus 600 times 3. What's that equal to?
2,400.
2400 negative. Which means I go from 4200 to 2400. How do I go?
Linear.
I have to go linearly with a slope that is smaller than the previous case. Okay, so in this case, if I'm sitting here and looking at it, they are not of the same slope, so I should probably draw it out better. Okay, so they are not the same slope. It's not a horizontal line either, so I'm starting at a larger slope. Why is it a larger slope? Because the value of the shear force is larger here, is 900. The value of the shear force is 600 here. So the slope is smaller. But it's a positive slope because my shear force value is positive. And the bending moment itself is a linear line because it's a straight line because the slope is constant. Now comes the tricky part. I need to go back to 0. Am I sure that I'm going to go back to 0? The only way I can do that is by calculating the area under this curve. I don't want to do that. I'm hoping to God that my calculations are correct. Okay? And then say that, okay, you're eventually going to go back to 0. If your calculations are correct, your shear force diagram will close. If your shear force diagram closes, your bending moment diagram has to close. Because it's nothing but the integral of the shear force diagram. Okay, so I know that my answers are correct based upon the shear force diagram itself. So I know that I'm going to go back to 0 here. Okay, because at the end of the beam, there is nothing else happening. Right? There are no couple moments at the end of the beam. How do I go? I look at the shear force diagram. The shear force value is positive and decreasing in a quadratic manner, which means that the bending moment curve is going to see a slope that is positive and decreasing in a quadratic manner, which means my bending moment itself is going to be a cubic. And so I'm going to go this way. My slope goes to 0 because my shear force value goes to 0 here, so this is 0 slope. I start off at a large value of the slope, so probably the same as, there should be some continuity there, so I apologize for that. Should be the same as the slope here, okay? My slope is decreasing. Why is my slope decreasing? This is because the value of the shear force is dropping from 600 to 0. What's the nature of my curve? It's going to be a cubic because my bending shear force diagram is a quadratic. So this is a cubic. And so until you specify, I would never know whether this is a cubic or a quadratic. So that's why I want you to specify. I want to see your thought process. Once again, what did we do? We started by looking at the three-body diagram, seeing that there is a counterclockwise couple moment. Magnitude 6,900, so I drop down first, all the way. Then the next stop, I have to look at the shear force diagram. Area under the shear force diagram has to be added with this value here. I'm adding it because the area is a positive area. That takes me to 1,400 negative. How do I go? Linear. Continue along the same line of thought. I have to take this area and add it to 4,200 because my shear force is in the positive x-axis. The shear force value is positive above the 0 x-axis. Straight line. Lastly, I know that my answers are correct because my shear force diagram closed. So I know that I have to go back to 0. Why am I going to 0? Because there is nothing else here at the end of the beam. There are no couple moments here. So I go in the manner of a cubic. Because the shear force is a quadratic, the slope of my cubic is decreasing because the shear force value is decreasing. Not many calculations involved, just inspection and looking at the equations of shear forces and bending. Next class I'll solve only one more problem of this nature, then we will go on to bending theory. Okay? Thank you.
Professor. Professor. Professor, I have a quick question.